In the weak law of large numbers, we saw a new notion of convergence come up. In this lecture, we're going to explore it and its relationship to other kinds of convergence that we already know. We're going to talk about convergence in measure. In any measure space, we say that a sequence of measurable functions converges in measure to a measurable function if the following holds true. For every tolerance epsilon greater than 0, the measure of the set where fn and f differ by more than epsilon tends to 0. The statement of the weak law of large numbers is that given a sequence of uncorrelated random variables with common mean and variance, the empirical average of those random variables converges in measure to 0. If the measure space is a probability space, we usually refer to this notion as convergence in probability. Now, convergence in measure tells us about how measure concentrates, but it doesn't tell us about where measure concentrates. And so it is weaker than the usual kind of almost sure convergence that we would like to have. Last time we saw a probabilistic example to demonstrate this, but in fact it's easy to demonstrate in a straightforward way examples of convergence in measure that do not converge almost surely. Here's one standard kind of construction. Consider a sequence of functions on the unit interval. They're all indicator functions. We'll start with the indicator of the whole interval, and then we slide an indicator along half the interval, and then we slide an indicator along a quarter of the interval, and then along an eighth of the interval, and so on. So if we want, we could give a formula for this. The function fn, where n is written dyadically as the sum of powers of 2 to the n plus some number k in between 1 and 2 to the n, this sequence of functions is defined to be the indicator of the interval from k minus 1 over 2 to the n up to k over 2 to the n. So that is for k between 1 and 2 to the n. Now that sequence converges in measure, in Lebesgue measure, to 0, because the Lebesgue measure of the set where f 2 to the 0 plus 2 to the n minus 1 plus k minus 0 is bigger than or equal to epsilon is, well, if epsilon is bigger than 1, then this function never attains that height, and so that's 0. Whereas if epsilon is between 0 and 1, then this measure is exactly equal to 2 to the minus n, the length of the one lonely interval where this function is not 0. And so, of course, that tends to 0 for any epsilon, which shows us that, therefore, this sequence of functions converges in Lebesgue measure to 0. Note, however, that this sequence of functions does not converge to 0 almost surely, because for any real number in the unit interval, the function fn will equal 1 on a non-trivial interval containing x for arbitrarily large n. No matter what x we choose, maybe this one here, the function f is non-zero at f9, and it will also be non-zero at some fn in the next sequence of dyadic intervals, and also in the following sequence of dyadic intervals. The n's for which f at that point x are not 0 get farther and farther apart, but there are infinitely many of them going up the tower, which means that fn does not go to 0 at x, or in fact on a shrinking neighborhood of x, meaning that fn does not go to 0 almost surely. So convergence in measure is certainly weaker than almost sure convergence. It's a little strange to talk about convergence with a notion like this. We're used to convergence meaning convergence in a metric space. For example, we might try to define a metric here. Let's say for fixed epsilon, we'll define the distance between two measurable functions to be the measure of the set where they differ by at least epsilon. But that's definitely not a metric for any fixed epsilon. It certainly is going to be 0 when f and g are not equal, in many cases. But in fact, it's worse than that. It's not even a pseudometric. It doesn't satisfy the triangle inequality. But it kind of satisfies the triangle inequality when we consider all the epsilons together. And this will highlight an important trick that we're going to use frequently when talking about convergence in probability. Let's for now define this d epsilon thing and look at the d epsilon distance between f and h. And we'd like to compare that to the distance between f and g plus the distance between g and h to see something like the triangle inequality. Well, we can do the usual thing and say, let's break up f minus h as f minus g plus g minus h. Now we'd like to use the triangle inequality inside here for the absolute value. And we can do that if we're careful. So note that the set of outcomes in our measure space, for which, let me just write the two difference functions as a and b, is greater than or equal to epsilon. Well, a plus b in absolute value is less than or equal to the absolute value of a plus the absolute value of b. And therefore, if this is bigger than or equal to epsilon, then this is also bigger than or equal to epsilon. So we therefore get a containment. The set where the sum of the absolute values is greater than or equal to epsilon contains the upper set. And therefore, by monotonicity of measures, the measure of that set is less than or equal to the measure of the set where f minus g in absolute value plus g minus h in absolute value is greater than or equal to epsilon. Okay, but what we wanted to have was the measure of the set where this function is greater than or equal to epsilon plus the measure of the set where this function is greater than or equal to epsilon. So how can we compare those two? And here's where the important trick comes in. So here we're saying I have two positive numbers, absolute value of a and absolute value of b, whose sum is bigger than or equal to epsilon. Well, if that's true, while it doesn't follow that one of them is bigger than or equal to epsilon, it does follow that at least one of them is bigger than or equal to epsilon over 2. Because if each of them was less than epsilon over 2, then the sum would be less than epsilon. We could do this with arbitrary sums, even infinite sums. If you have a sum of non-negative functions bigger than or equal to a sum of non-negative numbers, then at least one of those functions has to be bigger than or equal to one of those numbers. And we'll use that later on in this lecture. Therefore, this inside set here is contained in the union of the set where f minus g is bigger than or equal to epsilon over 2 and the set where g minus h is bigger than or equal to epsilon over 2. And again, by monotonicity of measures, that will be an upper bound. But also by additivity of measures, this will be less than or equal to the measure of the set where the absolute value of f minus g is bigger than or equal to epsilon over 2, plus the measure of the set where g minus h in absolute value is bigger than or equal to epsilon over 2. So that is the distance relative to epsilon over 2 between f and g, plus the distance relative to epsilon over 2 between g and h. So while this d epsilon thing doesn't satisfy the triangle inequality, the family of them together, considering all epsilons, kind of does. And we can actually make that precise by defining d0 to be the infimum over epsilon greater than 0 of that measure. Except that still is not a metric. It still does not separate points. But we can fix that by adding in an epsilon. And it turns out that that is a genuine metric on the set of all measurable functions, and it metrizes convergence in measure. A sequence of functions fn converges in measure to a function f if and only if this distance function between fn and f tends to 0. To be clear, it is a genuine metric only after we mod out by null sets, as usual. That is, we won't be able to distinguish between two functions that agree almost everywhere. Let's introduce some useful notation related to this. We'll call L0 of a measure space the set of all measurable, real-valued functions on that measure space, as usual, modded out by the equivalence relation of agreement on sets of full measure. And we will equip that set of all measurable functions, which we know is a vector space, by the way, with this metric d0. Now, by the way, we're not usually going to use that metric. We're going to use the definition of convergence in probability. That metric is a little bit finicky to work with sometimes. There are other metrics that we could use that give the same result in a finite measure space. For example, we could define a metric on the space of random variables, measurable real-valued functions on a probability space, as follows. The expected value of the minimum of the absolute value of x minus y and 1. There are others that we could use as well that will also give the same result. The fact of the matter is that convergence in this metric is the same thing as convergence in probability. And that is on your next homework set. Now it turns out that however you want to define this metric, it is complete. The space L0 of measurable functions equipped with the topology of convergence in probability is a Cauchy complete space. To be clear, since we want to write things in terms of convergence in probability instead of some metric constructed from that, let's define what it means to be a Cauchy sequence in this space. We say that a sequence of measurable functions in L0 is Cauchy in measure, or we might just write L0 Cauchy, if, for any tolerance epsilon, the measure of the set where fn minus fm is bigger than or equal to epsilon in absolute value tends to 0 as n and m both go to infinity. We're going to see in a few moments that L0 Cauchy sequences converge in probability. And in fact, they converge even better than in probability, which is probably the most important part of what we're going to prove here. Before we get there, let's explore some basic properties of this convergence. So suppose I have a sequence that converges in probability. Well, I've mentioned that convergence in probability is actually metric convergence, which means limits are unique, but it wouldn't hurt to verify that directly. So the statement is that if fn converges in probability to f and also to g, then f and g are equal, almost surely. We also have the usual respect for vector space operations in these limits. If fn converges in measure to f, and gn converges in measure to g, then any linear combination of fn and gn converges in measure to that same linear combination of f and g. And finally, convergence in measure implies Cauchiness in measure. Now it turns out that all three of these follow exactly the same outline of proof, and it is exactly the same calculation we did in deriving how the metric ought to be defined using the epsilon over 2 trick. So I'm only going to prove one of them and leave the others to you. I'll just do part 3. We want to show that convergence in measure implies Cauchiness in measure. So take our convergence sequence fn and look at the difference between fn and fm. As usual, we'll break that inside up as fn minus f plus f minus fm, and use the triangle inequality for absolute value to bound that by fn minus f in absolute value plus absolute value of fm minus f. Now we're interested in the measure of the set where this difference is bigger than or equal to epsilon, and by the exact same epsilon over 2 trick, if this is bigger than or equal to epsilon, since this is less than or equal to the sum of those two things, at least one of these two has to be bigger than or equal to epsilon over 2. And by monotonicity of measure, this is therefore less than or equal to the measure of the set where fn minus f is bigger than or equal to epsilon over 2, plus the measure of the set where fm minus f is bigger than or equal to epsilon over 2. Well, our assumption here is that fn converges to f in measure, which is exactly to say that for any epsilon, in particular epsilon over 2, this converges to 0 as n goes to infinity, and this converges to 0 as m goes to infinity. And therefore we have that the whole thing converges to 0 as n and m go to infinity, which is to say that Fn is L0 Cauchy. Parts 1 and 2 involve exactly the same kind of argument. Now here's the more technical persnickety part. If Fn is an L0 Cauchy sequence, then it converges to something in measure. Moreover, and here's the really important part, if Fn is an L0 Cauchy sequence, then there's some subsequence which converges to a measurable function almost surely. Let's prove that. Our assumption is that the sequence is L0 Cauchy, which means that the measure of the set where the difference between Fn and Fm exceeds any particular epsilon in absolute value tends to 0 as n and m go to infinity. So here's what we're going to do. We're going to apply that sequentially for each natural number k. We're going to choose an nk. I'm actually going to make it an nk plus 1 to show that we're doing this recursively, such that the measure of the set where fnk plus 1 minus fnk, the nk that we chose before, is bigger than or equal to epsilon, where that epsilon is going to be 2 to the minus k, is less than or equal to 2 to the minus k. So, for example, for k equal 1, let's just choose n1 equal to 1, and then we just need to find our n2 so that this difference being bigger than or equal to this epsilon, which is going to be 1/2, has measure less than or equal to 1/2. By this assumption, we can do that. Now, once we've chosen that n1 and n2, we need to choose our n3 when k is equal to 2, and we do it again, applying this property, this time with epsilon equal to 1/4, and so on down the line. And just to be careful, as we're doing this, we better choose nk plus 1 bigger than the nk that we chose before, so that the sequence of indices is a strictly increasing sequence. That's going to give us our subsequence. Now, the reason that we did this with powers of 2 is that this is a summable sequence of numbers. And so, therefore, we have that the sum, k going from 1 up to infinity, of this measure is finite. And since we have a sum of measures that are all finite, we can apply the Borel-Cantelli lemma, which will tell us that, therefore, the measure of the set where fnk plus 1 minus fnk is bigger than or equal to 2 to the minus k, infinitely often as k grows, must be 0. Okay? What does that mean? Well, let's let this set be E. E is the set of points in our measure space where fnk plus 1 minus fnk at that point exceeds 2 to the minus k infinitely often as k grows. So what the Borel-Cantelli lemma has allowed us to conclude is that on the complement of this measure 0 set E, fnk plus 1 minus fnk is less than or equal to 2 to the minus k for all large k. On the complement of E, this property fails to hold for only finitely many k, and therefore, eventually it holds for all large k. Now, how does that help us? We need to define a limit for this subsequence. And the way we'll do it is just by adding them up. We'll define f to be fn1 plus the sum k going from 1 up to infinity of the difference fnk plus 1 minus fnk. Now, on E complement, this property here shows us that this is a uniformly convergent sum. And therefore, since it's a convergent limit of measurable functions, this is a measurable function. We haven't defined it on E. Let's just say f equals 0 on E. It doesn't really matter. We know that that will still produce a measurable function. Now we just need to show that f is the limit of this subsequence on E, on this set of full measure. And that's going to follow because we constructed this as a telescoping series. You see, fn j plus 1 for any j can be written as fn1 plus the sum k going from 1 up to j of fn k plus 1 minus fn k. But we know that as j goes to infinity, converges uniformly on E complement to f. And therefore, we've shown that this subsequence, fnj, does converge to f almost surely. This f is a measurable function, and that proves the first important part of this theorem. Any Cauchy sequence in measure has a subsequence that converges almost surely to a measurable function. Now we just need to conclude from this that the original sequence converges in measure to this limit f. Well, to do that, here is the claim that we will show. For any index L, the measure of the set where that limit function differs from this term in the subsequence, fn L plus 1, by more than 2 to the minus L, is actually less than or equal to 2 to the minus L, which pretty much matches the way we defined the subsequence. To prove this, consider this event. And notice that this difference between f and fn L plus 1, by the telescoping definition of f, can be written as the sum k going from L plus 1 up to infinity of fnk plus 1 minus fnk. So what we're interested in here is the event that is bigger than or equal to 2 to the minus L. Of course, that sum is less than or equal to the sum of the absolute values. And now let's note, conveniently, that 2 to the minus L can also be written as the sum, k going from L plus 1 up to infinity, of 2 to the minus k. And now we use the same trick that we highlighted earlier, the epsilon over 2 trick, except now we have a countably infinite sum. I have a sum of non-negative terms which is bigger than or equal to another sum of non-negative terms. If that's going to happen, then at least one of these terms, indexed by some k, has to be bigger than or equal to the term over here, indexed by k. So that is to say, there must exist at least one k such that fnk plus 1 minus fnk is bigger than or equal to 2 to the minus k. And therefore, by the union bound for the measure that we've been using, it follows that the measure of the set where f minus fnl plus 1 is bigger than or equal to 2 to the minus l is less than or equal to the sum k going from L plus 1 up to infinity of the measure where the difference between fnk plus 1 and fnk is bigger than or equal to 2 to the minus k. But as we showed on the last slide, that is less than or equal to 2 to the minus L for all large L. And therefore, we can now conclude that the measure of the set where f minus an arbitrary fn is bigger than or equal to epsilon will be, again using the epsilon over 2 trick, less than or equal to the measure of the set where f minus fnl for any particular nl is bigger than or equal to epsilon over 2, plus the measure of the set where that fnl minus the fn that we started with is bigger than or equal to epsilon over 2. Now, by what we just showed above on this slide, this will converge to 0 as L goes to infinity. But by the L0 Cauchiness of the sequence, this will converge to 0 as n and L go to infinity. And therefore, since the epsilon here was arbitrary, we see that indeed fn converges in measure to f. That was a little technical and tricky, but it's a really important fact that we're going to use in the next lecture and beyond. Before we conclude, let's look again at the relationship between convergence in measure and convergence almost surely. We've seen that convergence in measure does not imply almost sure convergence in that initial example. However, as we just proved, it does imply convergence almost surely of a subsequence. Now in the converse direction, things are a little easier. If you have a sequence of functions that converges almost surely to some measurable function, then you do indeed also get convergence in measure. Let's prove that now. So suppose that fn converges to f almost surely. Then for any epsilon greater than 0, if I look at the set where fn minus f in absolute value exceeds epsilon for infinitely many n, that has measure 0. Indeed, the fact that fn goes to f almost surely means that on a set of full measure, fn minus f is eventually less than epsilon. Well, just to save some writing, let's let an denote this set where the difference between fn minus f is greater than or equal to epsilon in absolute value. So what we have is that the measure of the set where an occurs for infinitely many n is 0. But remember, we can write that infinitely often set as the intersection over k of the union with n bigger than or equal to k of an. This union means the set where an happens for some n bigger than k, and taking the intersection over all k means that an must keep happening over and over again. Now note that as k increases, this union is a decreasing set. So we're taking the measure of the intersection of a decreasing sequence of sets, and by the continuity of measures, that's equal to the limit as k goes to infinity of the measure of that inside union. But ak is contained in the union with n bigger than or equal to k of an. And therefore, the measure of the set ak is less than or equal to the measure of the union. And we've just shown that that goes to 0. Therefore, the measure of ak, which is the set where fk minus f exceeds epsilon in absolute value, goes to 0 for any epsilon, which is exactly to say that fk converges in measure to f. So, almost sure convergence implies convergence in measure. Convergence in measure implies almost sure convergence of a subsequence. We're going to use this relationship next time to explore how both of these relate to other kinds of convergence, L1, L2, LP in general, and use this insight to show the completeness of those metric spaces.